This is Physics 2 First Lab, estimating the excess charge on Scotch tape. The purpose of this experiment was to observe the electrical interactions between pieces of tape and apply physics to estimate how much excess charge is on each. In this lab, we used two models. For the experimental model, we used two strips of clear tape, a ruler, and two support objects to create some sort of charge tapes and suspend one above the other. And then we used a computational model where we modeled the same situation in GlowScript using Coulomb's law and force balance to calculate the charge on the tape. Determined that each piece of tape has a charge of 1.8 times 10 to the negative 8 coulombs. Each tape has a efficiency of 8.75 times 10 to the 10 electrons, and there are 4.56 times 10 to the 6 atoms per missing electron on each piece of tape. Fundamental physics principles. First, we have Newton's second law. In our experiment, the top tape stayed motionless, so the net force had to be zero. So F net equals zero, and this means that the forces acting on the tape on top were balanced. We also used Coulomb's law to relate the electric force between the two charged tapes to the amount of charge on each tape and the distance we measured between them. Finally, we used the gravitational force since gravity pulled the top tape downwards. For the initial conditions of our experiment, the tape had a mass of 0.2 grams, that is 2 times 10 to the negative 4 kilograms. Its strip was 20 centimeters long, which is 0.2 meters long, and 2 times 10 to the negative 2 meters wide. And the distance between the two suspended tapes was measured to be 3 times 10 to the negative 2 meters, or 3 centimeters. Since the top tape was motionless, the downward gravitational force had to be balanced by an upward electric force. We defined our system as the tape on the top and the surroundings as the tape on the bottom and Earth. So for calculations, we first calculated the gravitational force using the mass of the tape on the top and gravity, and this force pulls the tape downwards. Then we calculated the electric force, and since the tape was suspended and not moving, the net force had to be zero, and that means that the upward electric force from the bottom tape had to be exactly the same to balance gravity. And we found that the magnitude of this electric force is 1.96 times 10 to the negative 3 newtons, just as the gravitational force we found before. For the calculation of the electric charge, we used Coulomb's law and the measured distance between the tapes, which was 0.03 meters. And we solved for the charge on each tape by rearranging Coulomb's law formula, as you can see in that image. And this gave us that the charge per tape was 1.4 times 10 to the negative 8 coulombs per each piece of tape. And for calculating the deficiency of electrons, we divided the tapes charged by the charge of a single electron, giving 8.75 times 10 to the 10 electrons missing on each tape. And we also estimated the number of atoms per missing electron to be 4.57143 times 10 to the 6 atoms per electron. To support our experimental measurements, we created a computational model in GlowScript and in WebD Python that represents the electrostatic interaction between the two charged pieces of tape. And we represented each tape as a point charge, the bottom tape being the red one and the upper tape being the blue one. We represented their respective electric fields with arrows of the same colors of the point charges and the electric force acting on the upper tape with a red arrow and the gravitational force acting on the top tape with a green arrow. And through this method, as you can see, we were able to derive the same calculations and results as we did previously. Some assumptions we made throughout our experiment that might have caused some sort of error include that we ignored air resistance in a moving object. We also treated the long tape as if it was a point charge, with all the charge concentrated at the center of the long tape. We also assumed that each U tape had the same amount of energy, evenly distributed along the length of the tape. And we also ignored the effects of handling and the environment, such as the humidity on the charged tapes. For the discussion, if the charges of electrons and protons were to be changed, the observations would not change, since the tapes would still have the same charges, negative in the opposite case, and repel each other. And the tape would still be attracted to my hand, as my hand would now be positively charged and the tape negatively charged. And it is important to handle the tapes as little as possible to prevent the charges from neutralizing and external electric fields to influence the polarization of the tape and the results of the experiment. In conclusion, the experiment showed that charged pieces of clear tape exerted measurable electric forces, and using the balance between gravity and electric repulsion, we found that each tape carried a certain charge corresponding to a deficiency of certain number of electrons, and the GlowScript computational model helped visualize these results, and we determined that carefully handling was necessary to prevent charge loss, and that this experiment demonstrates fundamental principles of electric forces, charge distribution, and force balance.